Okay. Hi, everybody. Gonna do a quick introduction, and yeah, this is also being recorded. We disabled unmuting, so I would ask for people that want to ask questions to just put them in chat. I'm just gonna interrupt Luca during his talk, and he's gonna answer them. So a quick introduction. Luca Moschella is currently working on his Ph.D. at Sapienza University in Rome, under the supervision of Professor Rodolà in his research group for Gladia. They have a really cool logo, by the way, and he's also research intern at NVIDIA. His research focuses include, but are not limited to, geometrical deep learning, representation learning, reproducibility of models. So in this regard, today we're going to talk about the relative representations and how they enable zero-shot latent space communication. So thank you, Luca, very much for taking the time. And as mentioned, if somebody has any questions, you can just put them in chat and I'm just going to interrupt.
Yeah, thank you very much for the introduction, Martin. So let me share the screen so that we can start. Okay, you should be able to see everything. So this work is a collaboration between our group Gladia and Amazon with Francesco Locatello, but it was mostly done like internally, basically. As Martin was saying, this is about rel representations and how they enable zero-shot latent space communication. But let's start from the beginning just to understand what we are talking about. So we are in the context of neural networks, of course, and we define neural networks to be composed of two pieces, basically, the encoder and a decoder. So in general, we have some data in input to the encoder. It embeds the data into some sort of embedding. And then there is a decoder that takes this embedding and solves a downstream task. So in our definition, in this kind of setting, this is not only an autoencoder. We are talking about generic encoder-decoder models. So the decoder may have any dimensionality in output, and in general, we define it to solve some task. It could be generation, classification, or reconstruction. So the autoencoder is only a single class of one of these tasks, basically. So we will start by looking at a simple toy example to study the shape of the latent spaces. So let's, going back to these encoder-decoder models, let's define toy autoencoder. So in this example, we are indeed in the autoencoder setting. So basically, we have one image in input. We are using MNIST, that is a data set of digits, handwritten digits. So we have this image in input to the encoder. The encoder embeds the image in some embedding. In this case, the embedding is bidimensional. And then the decoder takes this embedding, these two numbers, and is able to reconstruct the digit. So this is our setting. We are training a network like this, a very simple network with a bidimensional embedding space on NIST. And this type of network has a very nice property, that is, we can take the embedding and visualize the latent space of this network without any dimensionality reduction. So we basically have one point in 2D that we can associate directly to an image without any artifacts. So we do the following, basically. We take the MNIST dataset, and on the left, and on the right, we are going to take another seed. So basically, we are training two autoencoders, as we described, the same kind that we described before, with two different seeds. On the left, on MNIST, and on the right, with a different seed. So there's shuffling, for example, different, but also the parameters initialization of the network is different. And any other randomness in the two networks is different. But the overall architecture, data, and task is the same. And let's see what happens. So here we visualize, as we did before, the same digits in the two spaces, again, without any dimensional reduction. So we are visualizing what is happening exactly. And as you can see, during training, the latent spaces evolves. The different colors here represent different classes of the MNIST. So for example, the orange one may be the 9. And of course, we are representing the same data. And these are two latent spaces of two networks at convergence. And they seem quite different. And this is quite surprising, right? Because we train the same network on the same data with the same task, with the same hyperparameters, and we get to two different latent spaces. Not completely surprising because we have different seeds too. So basically, ideally, we would like the latent space to be influenced only from these contributing factors, basically the data, the task, and some constraints. What do I mean by constraint? For example, if you have a VIE that has a latent space that is regularized to look like a Gaussian, of course, that space will look like a Gaussian. So that's a constraint. Another example is if you have an activation function that is a ReLU right before the latent space, of course, you won't have negative values in the latent space. So those kind of architectural constraints I'm referring here. But in practice, we have many other contributing factors that influence the shape of the latent space. So the data shuffling, the parameter initialization, the seed, in general, all the hyperparameters, for example, changing the learning rate will change the latent space. And the goal of this work is to be invariant to these factors because we don't like them. So we would like to have the same spaces for different networks that are trained in the same setting. So let's go back to our latent spaces. And I'm sure you noticed that they are different, but actually quite similar. So let's see one transformation that we can apply, a very simple one, so that the two spaces will be very similar. So let's start. So basically, we select two data points, the same data point, so two images, and we embed those two images with the two encoders that we train on the left and on the right. And we get two latent embeddings, basically, the stars in this example, the yellow and the blue one. Then for each other sample, for example, the orange dot, we compute the relative distance, the relative latent distance between the stars and the sample that we are considering. In this example, we are using the Euclidean distance. And then we perform a change of reference frame, basically, where we consider the orange dot to be represented by the relative distances. And this new setting, we basically transform the two spaces so that they are similar, very similar, and as you can see here. And this is the whole concept behind this work. So let's define a little bit more formally the things. We saw that source of variations in the training process induce distinct latent spaces. And one question that we must ask ourselves is, can we model how the latent spaces are affected, how they change from one training to the other, when we only change the seed, for example? And the answer is yes. Basically, we assume that a near isometric plus rescaling transformation T of the latent space is what correlates the two spaces. Here with rescaling, I'm referring to local rescaling. So basically, each embedding can be rescaled independently from the others. So it's already, it's not just an isometry, but it's an isometry plus this rescaling. Intuitively, basically, this rectangle that you see here that is rotating can also become a square. So basically, what we want to do is to have a representation that is variant to T. The flow is the following. We observe that there is a transformation. We assume and model that the transformation is this one. and we define a representation that is invariant to that transformation. And those are the relative representation that we are defining here. The algorithm to compute them is extremely easy. So we start by selecting a subset of anchors of the dataset. So a subset of the training set that we call anchors, basically. On the right, you can see that they can be, for example, 5 or 1. They are images because they are from the input space. Then we consider each other sample X in the data distribution that we are considering. We are not forced to be, of course, I mean, it's not forced to be from the training set, but can be any sample that follows the same distribution as usually in neural networks. Then we consider an encoding function E, and we embed the samples on the right so that we can latent codes. And we define the relative representation of X to be the relative latent distance, computed according to some similarity function. In this work, we use the cosine similarity as similarity function. And this is very simple to compute. They are just 3 lines of PyTorch, and it is differentiable. So that will be very useful in future. And there are 2 important properties that should be clear. So the first one is that the size of the relative representation depends on the number of anchors, not on the embedding dimensionality. So if you have 2 anchors, but your encoder outputs an embedding of size 100, your relative representation will have size 2, not 100. This property will be very useful when we will compare networks that have different latent dimensionality. And the second property is that the anchors and the similarity function influence the representation properties. What does it mean? Basically, we say that we are invariant to rescaled isometric transformation, but this is a consequence of the similarity function that we choose. So we choose the cosine similarity, and this function induces a property to be invariant to this type of transformation. If you choose another similarity function, you will have another property, another invariance in the representation that in other setting could be more useful. So if you have any questions, feel free to interrupt. We will start with the applications and how those representations can be useful. The first one is the semantic invariance. So say that we are given some words and we consider the embedding in different spaces. So I'm sure you know very well the fast text word-to-vec word embeddings. They are basically different ways to represent English words. And here we are visualizing different semantic clusters. So basically we choose 4 different words with very different meaning. We selected similar words to those 4 words. And in this way we obtain 4 different clusters. And each color represents a cluster, and we are visualizing the same words in both spaces. These are the absolute spaces. So what you get when you download the fasttext or word-to-vec word embeddings. If we do these relative transformations, what we observe is that actually they are very similar, basically almost the same. We also, in the paper, we also have some quantitative results with our retrieval task that shows that they are very compatible when we consider their relative space. And of course, they are very different in the absolute sense. So what we are observing basically is that latent spaces with the same semantics, meaning that they embed data that has the same semantic, are represented similarly in the relative space. So another application, completely different setting, is the following. So here we are on a node classification task. So we are dealing with graphs, and in particular with the Cora dataset. This is just a graph of paper and the references between papers, but not at all important right now. What is important is that it is a node classification task. So each node of the graph has a color, and we are given a good reference model. And this means that this model is able to predict the correct color for the nodes, and is very good at it. And this is given. We are not like aiming to obtain this model, but we want to exploit this model. And once we have this, we train other models to solve the same task. And we want to plot these models. So here on the left, let me explain this graph to you. So basically, we are on the y-axis, we have the performance, so how good the model is. The orange dot is the reference model. It is very good, so it is almost 1. That is the accuracy. On the x-axis, this is the latent similarity to the reference model, latent in the relative space. So these models are trained normally without representations, but then we convert the latent spaces to a relative latent space and compare the models with the reference one. Of course, here we are comparing the reference model with the reference model, so the similarity is 1 because it is itself. And on the right, there are the parameters, hyperparameters, and some architectural choices that we used to train this reference model. And we do the following thing. Basically, we change some of these parameters. So for example, here we change the seed, the epochs, and the dropout. And we train another model, this blue dot. This model will have a different performance, of course, and a certain similarity to the reference model. In this case, is 0.4, more or less. And we continue doing so. So we basically change the parameters and we obtain some other models. And what we observe is that there seems to be a correlation, basically. If we are similar to the reference model, we obtain good performances. So this is like a way to evaluate our models if we know and if we are given a good model, sort of a latent performance metric. And the correlation seems to be quite strong, at least in this task. So yeah, so if we are given relative models that are relatively similar in the relative space to a reference one, we have good performance. Be careful that if we have good performance, we cannot really say anything about this space similarity, because it may happen that there is a completely different latent space that is not the same in the relative space that still achieves good performance. That is possible, and it doesn't contradict the previous plot. And another interesting fact is that this correlation also happens while training. So let's see a single model, a single blue dot from the plot of before, while it trained. So here we are plotting the performance and the similarity across the epochs. And as you can see, the correlation is very strong, even while training, not only a convergence. And this happens on many models. I mean, it was like, it wasn't cherry-picked. Yeah, and the last application is zero-shot stitching. So let's see what
you before you start a new topic?
Yeah, sure.
Can you go a few slides back when you were showing I think it was like a list of the hyperparameters and some metrics of the model?
Yes, here.
So then, can you just elaborate really quickly about the encoder, the GCN2conv? Is this the graph convolution or?
Yeah, this is a graph convolution. Are two different types of graph convolutional encoders that takes an input, a graph, and produces embeddings for the nodes, basically.
Okay.
So they are similar in the sense that they both take the same input and produce the same kind of output, meaning not embeddings, but they behave in different ways. The architecture is different. Okay, thank you for the question. So yeah, zero-shot stitching. So let's start by a simple example of what we want to do. So we train two autoencoders independently. So they do not talk to each other, the top one and the bottom one. And we train them both normally and in the relative space, meaning that we get the embedding from the encoder, we convert it to be a relative embedding, and then we train the decoder on this embedding. And we can do this because as we saw before, the relative projection is differentiable. So it can be used while training. Once we have these models, we perform the following experiment. So we give to the first encoder an image, and it produces an embedding. But instead of proceeding as normal and feeding that embedding to the first decoder, we feed the embedding to the second decoder. And we ask ourselves, what will happen? And let's see, there are different things to consider. So in this slide, there are on the first row, the input image. Maybe here it's not visible, okay. On the second row, there is the normal autoencoder. And as you can see, it's just producing basically noise. This is expected because those autoencoders are trained independently. So if we train to take one component from one model and the decoder from the other and stitch them together without training or fine-tuning it won't work. The VIE is interesting because it seems to work. I mean, it's predicting realistic stuff, but the wrong one. Basically, as you can see, the 8 is reconstructed as a 7. The t-shirt has a bag. The pants have a shoe. Basically, what's happening here is that the space is regularized. So every point makes sense. The decoder knows how to interpret that point. The only problem is that the latent spaces are not compatible. So the meaning that the network associated to a point in the first model is different to the meaning associated by another network at the same point. So basically we are reconstructing, but just with the wrong meaning. Instead, in the relative case, the reconstruction are quite good. And as you can see, even if they were stitched from independent components, they seem to work quite well. And yeah, on the paper, we also show experiments on more complex settings, for example, on FIFA and ImageNet, and even on multilingual tasks. So for example, we are able to solve a task on the English language. The task was predicting the number of stars in Amazon reviews, given English reviews. And we train a model, a decoder, to be able to predict this number of tasks using pre-trained transformers. So there we are not trained the encoders. So basically we downloaded English transformer, Roberta, if I'm not mistaken, get the latent space, and train a decoder to predict the number of stars, all in English. Then we take that decoder that is able to predict stars and apply the same decoder without ever touching its weights, for example, on Dutch or Japanese text with the Dutch or Japanese transformer that produces some embeddings that are converted in the relative space that are fed to the same decoder. So we basically were able to train a model able to predict stars in a different language without ever seeing that language while training. Of course, this is not perfect. I mean, it's not achieving the same performance it would if it was trained directly on Japanese, but it's way above random. So this is kind of working. It's very interesting to me. And the underlying concept and of why this is working are the parallel anchors. So let's see why this is working. And why the relative representation makes sense, why we are able to stitch, communicate within different spaces. So the idea is very simple. So say that we are given two spaces, for example, the English and the Italian space. And we want to solve a downstream task once for both spaces. So we want a single component able to solve a task for both spaces. The idea is the following. Say that we are given some concepts, very broadly speaking, for example, cat and elephant. And then we consider some samples, different, any samples, in the two spaces, the English blue and Italian red. And what we do is the following. We want to represent the English sample, the blue dot, in terms of the English representation of those concepts. So we get the English embedding of the concept of cat, that is like cat, and the English embedding of the concept of elephant. And we represent the blue dot in terms of those anchors, what we call before anchors. In the second space, the Italian one, we represent the red dot in terms of the same concepts, but in the Italian space. So cat in Italian is gatto, so we represent the red dot using the anchors gatto and elefante. Basically, we are associating the same meaning to the different anchors. In this sense, they are parallel because we get relative representation in which each dimension is associated with the same meaning. So we can, given a partial correspondence, this is basically a partial correspondence within domain, we can get compatible representation. And bridging data modalities. So in a different work from our lab, Asif, we show that it is possible with some tricks, many more parallel anchors, because in the applications that I showed before, we were on the order of 300, 1,000 most anchors. Here we are on the order of millions, and some other tricks like sparsification. We are basically able to communicate between the latent spaces of images and text. So we get a huge text transformer, a huge image transformer that never talked while training. And we are able to solve a clip-like task, basically. Given an image, get the correct caption without never training a multimodal model. So basically, to conclude, we show that zero-shot communication between different latent spaces is possible, and it finds application in model stitching, in measuring the performance of neural models if we are given a reference model, and generalizing unimodal to multimodal models. And there are many further directions to explore. For example, defining different similarity or anchor choice may induce different invariances or properties to a representation that might be very suitable to other tasks or other contexts. Moreover, the relative space similarity is differentiable, so that could be used as a supervision signal while training. Think of a teacher-student framework, where the student learns from the latent space of the teacher. This is very interesting to me, at least. And that was all. So thank you so much for your attention.
Thank you so much. This was genuinely super interesting.
Thank you.
I enjoyed it very much. Also, your slides are really fantastic. It's some 3 blue 1 brown type of quality. So it was fascinating and also interesting. The last chapter, it seems like for some downstream tests we can get very similar results if we do some time of like transfer learning with an adapter, for example, and we just retrain like a small adapter, just a small number of hyperparameters. But it seems that this method that you proposed is basically very, very different. So it would be interesting to maybe just see what the difference would be if we use
Yeah.
what you talked about and like transfer learning with an adapter.
Yeah, I agree wholeheartedly. I mean, there is like a whole line of research that is like stitching, where they train a single linear layer to show that two different spaces are indeed very similar and correlated by a single linear transformation. But the thing that is very interesting to me is that without even doing that, somehow a similar representation emerges naturally from different independent models. So when you train a transformer on English and a transformer on Japanese, they end up obtaining similar latent spaces, even when you do so on different modalities, text and images. And to me, that is very interesting. And for sure, if you train a linear model to translate from one to the other, that for sure will work better, but that also requires compute and data, even more importantly than compute.
While working on it, what was kind of, because you mentioned data, so the first question that pops into my head is what is the like the biggest difficulty you ran into during working on this project?
So let me think. Basically, we were really lucky that most of the real world experiments were done with pre-trained models. So we just downloaded huge transformers from Hugging Face and used them and analyzed them and discovered that they end up learning similar things. So for sure, if we want to generalize to other domains or other modalities, that would require training good models. Because I mean, the basic assumption is that, or underlying the whole work, is that good encoders learn similar representations. And that requires that you have a good encoder. So, or you use a pre-trained one, and that is usually very good, or you need to train one. And if you need to train a one, for example, if you want another, I don't know, modality, data modality that is not available, you need both data, a lot of data, and but compute, a lot of compute. That for sure is so difficult.
Thank you for the answer. If somebody else has a question, they can write it in chat or interrupt me so I can ask them.
I would also have another question.
Sure.
You mentioned it in the last slide, but I also I thought about it while you were explaining the topic about knowledge distillation, because, for example, it seemed to me that while you were explaining the topic, for example, the relative representations, which can be used for semantic similarity in other spaces, especially when we are talking about different languages, it sounds like the relative representations are more efficient than the single models themselves. Do you think this can be used for efficient model distillation for knowledge, for model parameter size, for example, if the single models are very good and therefore also mostly very large, to get a smaller model? Or does the regularization process hurt the distillation process?
Okay, I think that's for sure a direction to explore, and we are actively exploring it.
Okay.
I think that the most promising direction in this sense are twice. I'm not sure if two good models can benefit from each other with this relative supervision signal. That would be interesting for sure. I'm more confident that if you are given a good model and you want to train a smaller model or a model with less data, that for sure could benefit from the knowledge in the good model. So you would be in the setting where you are transferring knowledge from one good model to another that wouldn't be that good. Instead, if I understood correctly, your question was about combining the knowledge of two models that are already very good. That would be harder, but also very interesting to me.
Okay. And across modalities, because, for example, if you compare the MNIST and Fashion-MNIST, this would be the more similar or more easier approach, probably, right? to get models with smaller number of parameters?
Yeah, the problem with, for example, comparing MNIST and Fashion-MNIST is that you need a semantic correspondence within domains, basically what we call parallel anchors. So you need to, in a sense, define which is a correspondent sample from one domain to the other. So in the case, for example, of images are caption, that is very obvious. Also, when you do multilingual stuff, you have a sentence in one language and a sentence in another language. That is like a parallel anchor. But when you consider MNIST and Fashion-MNIST, that is less obvious because their semantic is different. So I think that you can only communicate when you are training on data that has the same semantic, but represented in different modalities.
Okay. And do you also think like maybe you have to change the, like this is just me thinking out loud, I don't have any experience in this regard, but do you maybe have to change the regularization technique? Because for example, in the image where you showed the VAE and your relative representation, you also mentioned the regularization as a problem. Are there maybe other functions that could work better, or do you expect to be there other functions?
Yeah. Basically, the easiest setting for latent communication to happen is that when you have the same architecture, but you only change the seed. So if you have a regularization on both places, on both architectures, that's good. The problem is that when you have only on the first, you have a VAE, and on the second, you have another type of regularization that won't communicate. So in this sense, the best performance that we saw was when using very similar architectures. For example, Roberta Bayes, Roberta Small, if I remember. When you use different architectures, for example, on ImageNet, we tried with a Vision transformer and then with a RexNet that are completely different, because on one end we have transformer with attention and so on the other you have convolutions. It still worked, but it was worse than using similar models, and that is expected. So yeah, the question is that we still don't know which models are more compatible, which models yield compatible representation, and we don't even know why different architectures happen to yield the same representation. That is not intuitive to me.
Okay, yeah, but very interesting. Thanks.
You're welcome. Thank you for the question.
Is this something you're continuing to actively work on, right? Or is this a finished?
We are actively working on this line of research. Yes.
I have it's a kind of a nitpicky question, but just in the beginning, you were talking, I think it was something about the transformation of the latent space, and you called it near isometric, I think. And I was just interested if you can elaborate a little bit more.
Yes,
about
basically, the type of transformation we are invariant of is very peculiar. So we are invariant to an isometry. So think of rotation, reflections, and this sort of local rescaling. So you can think of a cloud of points that you can rotate, and then each point can be positively rescaled along the radius from the origin. So this is the kind of transformation we are invariant of, like exactly. Then, of course, when you, in that slide, we were referring to how few latent spaces are correlated, and that won't never be this kind of exact transformation. So there will be a small distortion, local distortion for each point that do not fall in this modeling, and that would be the near part, the near isometry.
Understand. Thank you.
Thank you.
Because I don't see an additional question in chat, we usually ask people at the end to tell us maybe 3 interesting research papers that they have read recently. I mean, if you can think of 3 on the top of your head, you can just tell one, or just some interesting subject.
Yeah, I mean, I'm very interested in analyzing, this work analyzes latent space, right? We saw that different models have similar latent space. There are other works that analyze the parameters of the model and show that also the parameters are similar. One example is this Git rebasing that was accepted at iClear. And there they show that if you train a model twice, there is a permutation symmetry between the weights, and they are actually the same up to this permutation, so they can merge models. That is very interesting for sure.
Thank you. I'm gonna ask once again if somebody else needs something to ask, they can ask it now. And if not, I want to thank you once again. This was generally really interesting, very enjoyable. And yeah, I was it's a very nice mixture of basically all different types of like methods and subjects, and it's riveting stuff. So yeah, thank you. It was very interesting.
Thank you so much for having me.
We are going to upload this to YouTube so people can watch it if they weren't able to join. And thanks to everybody for joining. Thank you once again for coming. And
thank you.
Have a nice night.
Goodbye.
Thank you.
Bye.
Bye.